Section 3.1 is about solving a system of equations by using the graphing method. A system of equations is when you have two or more equations that have the same variables. Here you see my equations both have x and y. To solve that, you find an ordered pair that satisfies both equations, and one method to do that is by using the graphing method. So I'm going to start with the first equation and graph it. The easiest way to do that is to isolate the y, put it in slope-intercept form. So here we have y equals mx plus b. So looking at this form, I can see my slope is -2, which I'm going to write as a fraction -2 over 1, because that's going to be my rise over my run. And my y-intercept is 5, which is an ordered pair of 0, 5. So I'm going to go ahead and graph that. Start with 0, 5, put a dot there, that's the y-intercept. And my slope is -2 for the rise and 1 for the run, so I'm going to go down 2 to the right 1. Down 2 to the right 1, and I'm going to graph that. So there's the first graph. For the second graph, x minus y equals 1. Again, I'll isolate the y, this time subtracting x. So negative y equals -x plus 1. I don't want a negative y, I want a positive y, so I'm going to divide everything by -1. So positive y equals positive x minus 1, which means my slope is 1 over 1. And my slope, or my intercept, is the point 0, -1. So we'll graph 0, -1, and then the slope is 1 over 1, or rise over run. So I end up here also, so I'm going to graph that line. We can take a look at our lines and see if there's a place where the lines cross, and it looks like they cross about right here, and that would be point 2, 1. Now we can't be sure when we graph that 2, 1 is the actual solution. So we're going to go back to our original problem and plug 2 in and see if it works, and plug 1 in. So 2 times 2 would be 4 plus 1 is 5, so it works in the first. And 2 for x minus 1 for y equals 1, so it works in the second. So we know that our ordered pair, our solution of this system, is the ordered pair 2, 1. As we continue to practice graphing, we're going to use this real-world scenario to show you one of the ways that systems of equations are used. Here we have a band that's planning to record a CD, and their initial startup cost is $1,500, and each CD is going to cost $4 to produce. So we're going to build an equation for what the cost of their CDs are to make. Well, each CD costs something. I'm going to call that Y, and it costs $4 times the number of CDs they produce plus an initial startup cost of $1,500. So there's my first equation. It costs them 4 times the amount of CDs plus $1,500. And I'm going to compare that to the income that they make. So another equation, we could say that their income is $10 per CD. Now there is no starting cost for that, it's just $10 per CD. So this is their equation for income. We're going to take both of these equations and graph them and find out when it's going to be profitable for them to make these CDs. So since we're going to graph these two, we need to set up labels on our graph down here. So I'm going to take and I'm going to make each one worth 50, and I'm going to jump from 100 to 200 to 300, 400 to 500. And we'll call this number is the x value, so this is the number of CDs, because that's the same each time. And on the side, we're going to say a dollar amount. And it's either a dollar amount that we cost to make the CDs or a dollar amount that we receive. Now this is going to end up being in the thousands, so I'm going to make each one 500. So this will be 1,000, this will be 2,000, 3,000, 4,000, and 5,000. So that's how I'm going to set up my graph. And now we're going to graph both of these lines. This one's already in slope-intercept form, so we can see that the slope is 4. Call that 4 over 1. And we can see that the y-intercept is 1,500, or 0, 1,500. Now it's easy enough to find 0, 1,500. That's right here. So that point's easy. Now, doing a rise of 4 over a run of 1, that's difficult, especially when we have units here that are so big. So it might be a better way to go by simply plugging in an x value and getting a y value. So I'm going to plug in maybe 300 for my x. And I'm going to just find a second point that exists on this line, And that's going to be easier, I think, than graphing the y-intercept. So this will be 1,200 plus 1,500. So 2,700 is the final cost if they make 300 CDs. So I'm going to get 300, 2,700. Well, 25 is there, so 27 about there. I'm going to graph that line. Now my second line, my slope is 10 over 1, which again is too small. And my b, my y-intercept, is 0, 0. So I know this is going to start at the origin. So I'm going to begin my graph right here at 0, 0, but I'm going to plug another value in. Let's do 300 again. And if I can plug 300 in for x, I can see the y is 3,000. So 300, 3,000 is my second ordered pair, and I'm going to graph that. So if you do the graph well enough, you should notice that they cross right here. And that looks at about 250 CDs, and then $2,500. So it appears as if the break-even point is this spot here. That means any more than 250 CDs sold, and they're going to make a profit, because the profit line actually goes up steeper than the cost line. So at this point, they'll start making money. Here you see a summary of systems of equations. When you graph two lines, they don't have to cross. The two examples that we've just done crossed. And when they do, we know that there's one solution, and the solution exists where the two lines intersect. Now there's some names that we have for that. We call those kind of lines consistent if they touch, and we say independent if they touch in one place. Now those two lines could also be drawn right on top of each other, and that's what you see here. You see two lines that are drawn right on top of each other. And if you see that, there are an infinite number of solutions because the two lines touch each other everywhere. And we call that consistent because they touch, and dependent because they touch in all the spots. And the third possibility when you graph two lines is those two lines could never touch at all. And we say that those lines have no solution. There's no point in which they intersect. And we call those kinds of lines inconsistent. So here we're asked to graph the system and then describe it. Give the vocabulary words consistent and independent, consistent and dependent, or inconsistent. In other words, how many solutions exist when we graph these. Well, here are two equations. I like to write them out side by side and then solve them separate. So here I'm going to isolate the y by subtracting the 9x. So negative 9x plus 24. And then I'm going to divide by negative 6. So we'll have y equals, now 3 goes into both of those, so this will be a positive 3 over 2x. And 6 goes into 24 4 times, so minus 4. So that's what my equation ends up being. And I'll do the same thing with the other equation. 6x minus 4y equals 16. Again, I'll isolate the y. So we'll get a positive y equals 3 halves, because 2 goes into both of those, and then minus 4. Now here's an example of a problem where I don't even have to graph, because I look at both of those equations and they're exactly the same. Which means I'm going to create the same line. Now I'll graph it just so we can get practice here. Negative 4 is my y-intercept, and then up 3 to the right 2, up 3 to the right 2. So it'll look like that, but both equations will cause that graph to be drawn. So we would say that there's infinite many solutions. Sometimes we'll say all real numbers, but what we're asked in this problem is to use the vocabulary words. Well, they touch, so we know it's consistent. And they touch everywhere, so it's consistent, dependent. Here's our last example. You may want to pause this and try it for yourself, and then come back and see the answer. So here we have our solution. We isolate the y over here, get negative 3/4 x plus 3. Isolate the y over here and simplify negative 3/4 x minus 2. You might notice that the slopes here are the same, which if you know about slopes will tell you that these are going to be parallel. I've graphed them both over here to verify, and you notice they don't touch at all. So if we were asking for the number of solutions, we would say that this system has no solutions. Now what are the vocabulary words for that? Well, the word we're going to use if they don't touch at all is inconsistent.